Good evening and welcome to BrisScience June 2024, and what a fantastic turnout we have tonight. I am your MC for this evening, Joel Gilmore, and thank you so much for coming out this evening. If this is your first time here, BrisScience is a free series of public lectures brought to you by the University of Queensland, where we aim to bring not just the best scientists, but also the best speakers to share and communicate their findings with the audience of Brisbane and through the wonders of Facebook and YouTube, the world. I would like to start by acknowledging the traditional owners of the lands which we're meeting tonight and pay my respects to elders past and present. And of course, as we talk about astronomy, of course, the Indigenous peoples all around the world were some of the first astronomers to study and record astronomical events through the oral history of those people, and things that we're still learning from and discovering today across the world. Tonight, we, of course, are going to have our speaker in a moment. A few little bits of housekeeping. First of all, if you have a mobile phone, very important you turn it to silent, because we want to have our focus, but also don't turn it off, because tonight there'll be an opportunity to ask questions of our speaker through this wonderfully timed QR code. If you scan that code, it'll take us to our page where you can put your questions in, and after the talk, we will get through as many of those as possible. But there will be the opportunity for some further discussion. We're going to have drinks and nibblies outside, so we'd love for you to hang around, chat with our speaker, and of course with yourselves, and discuss the things that we've learned this evening. All right, let's get into it, because tonight, I know we always say our speakers are fantastic, but we have a speaker who is literally out of this world. Thank you. Professor Trevor Ireland is a University of Queensland planetary scientist who has been studying meteorites for over 4.5 billion years. Oh, no, sorry. The meteorites are over 4.5 billion years that he's been studying. His expertise spans from geochronology to cosmochemistry as he seeks to answer some of the deepest questions about the formation of the solar system where we live. So for a talk that will only make you space out in a good way, please put your hands together for Professor Trevor Ireland.
Thank you for having me. Great turnout. It's a lovely evening tonight in Brisbane. You can see the moon, the crescent moon up in the sky, and unfortunately all the planets are coming up in the morning, so that was one of the things I was going to bring across straight away. But first, yes, in terms of what I do, I'm a geochemist, so I generally take rocks, crush them, destroy them, and ask questions of them and force them to tell me answers. And the answers are usually much easier coming out of the rocks than they are coming out of students, so it's a bit of an issue as we go forward. So I also am privileged to have an association with the Japanese Space Agency JAXA through the Hayabusa missions, which I've been working on for 20 years now, and also the OSIRIS-REx mission from NASA as well. So I'll put that for full disclosure that I actually do have some association with these guys. So let's start off. What are asteroids? I'm sure most of you can answer that reasonably well, and I'll give you some preamble on that and then show you some good pictures of what asteroids actually are. And going back to that lovely crescent moon in the sky, every once in a while you look up in the sky and you see all sorts of things going on. And as we were talking about, the Indigenous peoples knew the sun and the moon, the Mercury, Venus, Mars, Jupiter, Saturn, because these are the wanderers that walked across the sky. And every once in a while you could go out and this was in Canberra in 2008, you can see Mercury, Venus, Saturn, Mars, Jupiter. And the full moon was also up. And lo and behold, as I was taking the photos, the International Space Station flew by as well. So a very auspicious night and a great collection of photographs. But then you can go out a couple of years later, different time, different assemblage of planets. Here's Jupiter, Venus, Mercury and Mars in this sort of weird assemblage here. And you could just imagine the ancients sort of thinking, ooh, what's this going to bring? This does not necessarily look good. And so the planets have been messengers of telling us what we should be doing, and at various times what we shouldn't be doing. So if we look at the planets, what do we want to find out about them? The first thing people wanted to find out about them was how far away are they and what's really going on. And to cut a long story short, we'll start at, let's go back to that one. We'll start with a heliocentric solar system from Copernicus, 1543. I could tell a story, I will tell a quick story on Copernicus. So Copernicus is well known for developing the heliocentric solar system, putting the sun at the center. And the reason for doing that, it was already argued, well, it's just simpler than putting the Earth at the center. There's nothing physically wrong with what was going on before. It's just a bit easier. But he was a bit worried about publishing this. And so Copernicus actually died in 1543. So the last thing he did was publish his manuscript. And so this is the classic case of publish and perish. So the distances of the sun. So let's jump ahead a little bit. Kepler's laws, and I'm sure you all know Kepler's laws off by heart. I put them up here so I didn't forget them and embarrass myself. Copernicus wanted circular orbits. Kepler said the orbits are ellipses with the sun at one of the foci, and this cleaned up one of the big issues with actually having a geocentric solar system, that you had to have these things called epicycles and make the planets spin on their tops before they moved on. And it's like, well, that's a bit weird, physically a bit unrelatable. Orbits sweep equal area with equal time, and what this says is if you have a very elliptical orbit, as the object gets closer to the sun, it speeds up. So we see that with comets. So comets are, there's a comet coming, it's coming, it's gone. And you hear that all the time. And it's sort of the northern hemisphere, southern hemisphere transitions and things like that, which are really great. The one, oh, here we go again. The one which is used for figuring out how far away the planets are is this little relationship here, t squared over r cubed. So t is the period of the orbit, r is the radius of that orbit, and that's going to equal a constant. And so you can do the magic thing of making 1 year, 1 AU, constant equals 1. So if you make Earth 1, it all falls out. And so all you have to do then is measure the period of Mercury going around, measure the period of Venus going around. How long does it take Mars, Jupiter, and everything else? How long does it take to get round? And you come up with these relationships that Mercury's at 0.4 AU, Venus is at 0.7, Earth, of course, is at 1, Mars at 1.6, Jupiter 5.2, and then 9.5 for Saturn. And so if you look at this in terms of, cut a long story short again, if you look at these relationships, you can come up with this weird mathematical relationship, which is not really well explained even now, that you can put this formulation, r equals 0.4 plus 0.3 times k, where k is a constant, and that constant is 0, 1, 2, 4, 8, 16, 32, in which case you get 0.4, 0.7, 1.0, 2.6, 2.8, 5.2, 10.0. So you've pretty much got the right spacings of the major planets, the wanderers. The big question is, well, if you do that, then this formulation, you end up with something at 2.8. And this was noted in the 18th century, so by Johann Bode, who at age 9, I like putting this up in front of students, just to make them feel inadequate. At age 19, published on a solar eclipse. So his first publication was when he was 19, and then within 2 years, he had written the second edition of his astronomical compendium. I'm not going to read the German. It translates to Instruction for the Knowledge of the Starry Heavens, in which he noted a gap in this orderly progression. After Mars, there follows a space at 2.8 units. So he noted this, in which no planet has yet been found. Can one believe that the founder of the universe has left this space empty? Certainly not. And so this, of course, invigorating, we should go and have a look there, maybe we'll find something. And so various people have noted this, and this sort of became popular in the late 18th century to actually go out and look. And then Herschel in 1781 discovered Uranus at, oops, no, they can stay there, that's all right. No, let's go back. Laser. Herschel, 1781, discovered Uranus at 19 AU, and so this was then the next element in that sequence. And so, ooh, this really must be good. And so everybody noted the Titius Bode law, and so it's like, well, let's go and have a look a bit closer to see what we can find, and sort of let's get a committee together and have an amalgamation of all these scientists and try and figure out what is actually at 2.8U, because we want to be a planet there, and nobody's discovered one yet. And one of the people I invited was this guy, Giuseppe Piazzi in Palermo, Sicily. He was selected to join the group, but before his invitation arrived by email, he discovered a moving star-like object which he thought might be a comet. It's like, well, it hasn't got a tail, why should it move? But maybe it's going to get close to the Earth and so forth. And he observed it 24 times up to February 1801 at exactly the predicted distance, 2.77 AU. Great. He observed it through a telescope, but he couldn't actually see what was going on. It didn't resolve into a disk. So if you look in the telescope and binoculars or something like that, you look at those planets in the sky, they're pretty much solid disks. You can see them even when Mars is way far away on the other side of the solar system. It sort of still resolves into a disk. Not very exciting, but it's a disk. So these things were regarded as point sources of light, and so Herschel of Uranus fame suggested the term asteroid, which is star-like, even though the asteroids move like planets, and they're way moving against the background of the stars. So over here are a couple of illustrations, one of the constant star background and an asteroid moving across it, and the other looking at the asteroid itself and watching the stars flash by. And the asteroids are orbiting the sun, so they've got nothing to do with stars. And so this asteroid term has been a total mislead for centuries. But the object Piazzi was looking at is Ceres. It's a small object. It's only 940 kilometers across. And in that useful unit that we all love in arc seconds, it's about 0.85 arc seconds. I have no idea what an arc second looks like, but I do know what Mars looks like. If I look up into the sky and see Mars, it goes from 3.5 to 25 arc seconds, so it's way smaller than Mars. It has an apparent magnitude of 6.6 to 9.3. We can't see beyond 6, so it's black, basically. We can't see it. And it's actually a dark object. It's actually got a very low reflectivity. And Ceres is now up here against the moon and the Earth. It's now called a dwarf planet, which again is a committee decision to say that it's massive enough to be round, so it gets the designation of planet, but it's not massive enough to have cleared its orbit, and so it's now regarded as a dwarf planet. So this is the best optical image we had before we actually went there. So this is one series from the Hubble Space Telescope, and you can see it's sort of motley, and I said it was dark, and so this has all been enhanced to get the light up. But there's not a lot going on there. There's not a lot you can actually see happening. And after Ceres, there were a whole swag of other asteroids discovered, or 4 within a couple of years. Pallas, Juno, and Vesta by 1804. 5 Astrea was not discovered for another 40-odd years. Then there was 300 by 1890, 1,000 by 1920, 5,000 by 1990. And then something funny happened. We got interested in these things might be coming in to see us and visit us. And so we want to know where they are, how stable their orbits are. And so there's a lot of cameras put on telescopes up there, just a nice small 2-meter telescope, take these sky mapper images and try and figure out where all the small bodies in the solar system are and whether they're going to come down and cross the Earth orbit. And so now there's something like 1.3 million with a numbered designation. So there's a lot of them. So this is a sort of a cluster map of where they all are, and you'll notice that each one is represented by a pixel, which does not have enough resolution. So looking at this diagram, I wonder, well, how did we ever manage to get Voyager out beyond Earth, Mars, we're not going there, to Jupiter? But they're very few and far between. And you can prove that to yourself just by looking out along the ecliptic. You don't see the stars going away when you look out there. You see starlight all the time. And it's actually important when we actually do get starlight crossing one of those asteroids, because they like measuring sizes and things like that, and it's all very exciting. So there's also orbits on the inside and outside. So inside, these things have been scattered down inside the orbit down to the Earth orbit, this blue line down through here. So most of these have been because Jupiter gets involved with all this material and this junk, and Jupiter's up here somewhere, and in this position at 60 degrees behind and 60 degrees in front of the Trojan asteroids, and these are in a gravity lull where you balance out velocity and gravity, and so they're stable there. And there's a mission going out to see it. It's Lucy, I think, going out to visit those Trojan asteroids, and so in 5 or 6 years or something like that, we might get some images back from those. The asteroids move around. They're not just stable, and that's one of the reasons why we have those Earth-crossing asteroids, because Jupiter's sweeping them up, and if you get into the wrong resonance, the broom comes through and cleans you out. And so that broom occurs at 3 to 1. So for every 3 orbits of an asteroid to 1 orbit of Jupiter, Jupiter says you're mine, and you're going to get busted out. And if you want to lose energy, you go down into the inner solar system. And so there's a couple of dips as we go along, and then at 2 to 1, it's a major sort of one. So most of the asteroids are between 2 to 1 resonance down into this leading edge area, which is affected by Mars. So the take home for this is that the solar system, the main asteroid belt is the solar system dust bunny. So it's sweeping stuff around. It did not let it aggregate into a planet. And so one of the big questions is how many asteroids were actually there in the first place, and we're not going to find that out. I suppose somebody can model it. But even the giant planets appear to have moved about a bit, and so there's some argument now that some of the meteorites actually formed out beyond Jupiter, and then when Jupiter moved out, it pushed them in, things like that. And so the solar system is a very dynamic place. It isn't just as you see it now. Early on, when things were aggregating, there was a lot of material about, and there was a good chance that things are going to move around. So, after all that, what are asteroids made of? Well, cut a long story short again, too small to be anything but solid rocky bodies. So they could be icy, but get into sort of round Earth orbit, you're getting up with solar radiation over 100 degrees Celsius, all the water's going to evaporate. So these have got to be rocky bodies. We can observe them from Earth. A lot of them are small, but we can actually see light reflected off them. We can get radar reflected off them. And one of the classic things we like doing it with them is actually looking in the near infrared, because there's a number of spectral features there which are very important. So if you look at the mineral olivine, it looks green. It's green because it's absorbing red. And so the near infrared spectrum of olivine, and this one's a mixture of olivine and pyroxene, has a big dip at about 1,000 nanometers. And so that's where it's absorbing. That's part of the reason why it looks green. And the other thing we can look at is albedo, the reflectance. How much light, if we shine the torch on it, how much do I get back? Looking at you guys, not much. So we have these absorption bands, and we just have albedo and brightness. And so you can use these to sort of classify. And the original classification by Clark Chapman came up with 3 major types. He had C for carbonaceous, S for stony, and then he had unclassified. So he didn't even have the metal ones, it was just unclassified. So he had 3. So what do? Then you get a PhD student involved, and suddenly there's 23 subunits, because that's what PhD students do. They split everything up to increasing levels of detail. So we now have a whole heap more, and there's the 3 major types in terms of asteroids, the C, the carbonaceous, stony, and the metal asteroids. So C-type. So here's the spectrum, really boring. It's flat and smooth, so no mineralogical effects at all. And it's dark. It doesn't reflect much light at all. And so I'm doing this somewhat in isolation for what we think this is, but this is how it was originally portrayed, that these spectra are basically quite simple. The grey bands up here are sort of disturbance caused by terrestrial atmosphere. So this 2.5 millimeter region and 2.5 micron region is water being absorbed in the Earth's atmosphere. So you can't see that. So if you want to do these properly, you go outside into orbit and get them. So this spectrum is very common. It's very boring and it's very common. So the type asteroid is known as 10 Hygeia. It's the fourth largest asteroid, so 430 kilometers across, and it's the most common type, 75%. The stony types, suddenly you can see something interesting. There's a dip, which is related to that olivine and pyroxene. And so otherwise, it's actually quite a steep spectrum. If you basically back those out, it's quite a steep spectrum. And looking at this from 0.5 up to about 0.8, which is about good red, this is quite steep, and so this is going to be a red signature. That's why these asteroids look a little bit red when you look out at them optically. But they do have these absorption features around 1 micron and 2 microns, which are related to olivine and pyroxene. So these are the stony meteorites, stony asteroids. The largest of these is 15 Eunomia, 330 kilometers, and around 17% of asteroids have this signature. So we've already covered quite a few of the asteroids. There's not many left we can actually cover. But one of the interesting ones is the M-types. These are metals. These are potentially old planetary cores. So when some of the asteroids differentiated, they got a metal core like the Earth did, and then you just bash the whatever out of them, remove the mantle, and you can actually expose the metal core. So these things get absolutely roughed about by collisions in the early solar system. But these ones, again, the spectrum's fairly smooth, quite steep, and so it's going to be red again, looking at this. The inference of these iron-nickel doesn't come from actually that image. It comes because if you look at the radar reflectance, they're very bright in radar reflectance, and so they're all very dense. And so the way to get density up, just look at metal. And these are the third most abundant type, probably less than 5% of asteroids. So we've got these near-infrared spectra. We've got sort of a rough association with olivine and pyroxene. What do we know about olivine and pyroxene from space? We know space rocks, we know meteorites. So we can go out and pick up meteorites, and people did that, and they spent a lot of time crushing and abusing rocks, the meteorites, and getting the reflectance spectra, and lo and behold, you can come up with really good associations. I'll just leave it at that because we'll spend way too much time talking about individual meteorites. So this comes up with one of those good tongue twisters for Friday night, the spectrophotometric paradox. Can you say that? Whoops, I'll let you read it. Spectrophotometric. Way done. Well done. So the spectro refers to the spectrum that we're collecting. Photo means light, and metric says we measured it. That's what it's all about. And so the spectrophotometric paradox is that the C-type asteroids are the most abundant, but they're possibly related to the carbonaceous chondrites, but the carbonaceous chondrites are a very rare type of meteorite, and so we've got this paradox that needs to be solved as to why we don't see more carbonaceous chondrites of most of the asteroids C-types. So what's going on is what that says. So let's have a quick look at meteorites. It's not going to be much. So these are what the analogues are for those different types of asteroids. So Murchison is a carbonaceous chondrite. It's black. It's got inclusions in it. It's got little chondrules in there, little round silicate spherules. It's certainly a stone meteorite, but it's not the S-class stony type meteorite. It's dominated by this matrix, this dark grey matrix, and that matrix may have originally been the stuff out of which the galactic cloud formed very early in the solar system. The problem with these guys is that they saw a lot of water on their parent bodies, and so it's now hydrated. It's basically now dirt and clays and things like that, rather than the original stardust type material which we'd like to study. The stony meteorites, this is one here. is full of these chondrules, pyroxene, olivine. They're the ordinary chondrites, and the ordinary chondrites are ordinary because they comprise about 85% of all meteorites. In fact, if you go out and pick up if you find a meteorite and you go out and pick it up, there's a 1 in 3 chance that it comes from a single parent body out there somewhere, which is dumping stuff down on top of us. And then we have the metal guys. This is Henbury craters out by Alice Springs. And these are, well, let's go on. They're solid metal. So here's Murchison in a bit closer detail. So the big important thing about the carbonaceous chondrites is this dark matrix, because that's rich in organics and it's rich in water. And so one of the possibilities is that those organics rained down on the Earth and became some of the seeds for life. And so there are even amino acids occurring in Murchison. They're not the signature of life, though. They're all way too short, and they're left-handed and right-handed, whereas we're all left-handed, organic chemistry. So there's some step we're missing in there which is important. They're also rich in water. And so one of the things is, well, if the Earth accreted hot, which we think it did, there's a magma ocean, all the water boiled away, broke up and whatever. Where did the water come from? There's a possibility that it came from the asteroid belt and reseeded all the water late on. Ordinary chondrites, these are dominated by chondrites. They don't have much matrix at all. So these are known as dry meteorites because they're probably from the inner solar system. They also have some iron, nickel, metal through them. They're the most common type, hence ordinary, and they're about 85%. Iron metal meteorites, composed of iron, nickel, metal. If you go out looking for a meteorite, the chances are you will find one of these. You will not find a stony meteorite, because as soon as it rains, well, it never rains in Queensland, but as soon as it rains, they start breaking up. The carbonaceous chondrites might last a week. Ordinary chondrites might last a year, except if you go to desert environments. And so there's a lot of these found in northwest Africa and Antarctica, because there's not much liquid water down there either. So the issue with the iron meteorites is they simply don't weather away. They're like the natural stainless steel. And so you've got Tutankhamun with his dagger. There's a dagger of meteorite steel. People would make swords out of it, magic swords, because it's from a space rock. It's like nothing better than to see, oh, here comes my sword now. Comes in, bang, lands in front of you, get out, thump, 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 thump. I've got a sword of stainless steel. It doesn't rust. So if you've got this magic sword that doesn't rust, that's going to scare people. So how many meteorites are there? Ugh. Well, from the ones that have been reported, and I know a few of you have probably picked up a few and haven't reported them, there's about 50,000 of them classified, around 1,000 falls. So a fall is when I see my iron meteorite coming in and I'm going to collect it. So it falls at your feet, you go, and it's picked up, and we know it's a fall because there's all sorts of radionuclides in it. So out in space, nasty things happen and gets exposed to cosmic rays, and you have radionuclides in them. So they actually come in radioactively hot. The most of them come from desert finds, northwest Africa and Antarctica. And out of these, we think there's only about 200 parent bodies represented. So a lot of these meteorites come from the same body. Hence, I think it's 30% comes from the H5 chondrite parent body. But through various chemical associations, we can narrow it down to something like about 200 parent bodies. And of course, the parent bodies are the asteroids. And so we're sort of underrepresented to a certain degree with the diversity in the meteorites compared with the potential diversity in asteroids. And there's something like 1 million asteroids which are over 1 kilometre in size. And so they become increasingly important if one of them comes down onto Earth. So one of the classic occurrences was this asteroid 2008 TC3, which was the first object we saw before it actually came in. So, everybody's gearing up for these observations, but this would have been picked up by radar. It's like, ooh, there's a Doppler signal. Ooh, it's coming in at 15 kilometres per second. Oh, it's all right, it's coming in at Sudan. Nobody cares. It's not true. We cared a lot. We were really interested in this thing. And so it was seen 20 hours in advance of the entry, and that 20 hours allowed the full orbit to be reconstructed. It puts it out, originally coming out beyond, remember Titius Bodler, 1.6 AU for Mars. So it's coming out beyond Mars, 1.716, somewhere in the inner asteroid belt. And there's various other parameters you get. The eccentricity is really quite eccentric. That's because it's getting dumped out and it basically came down onto Earth's orbit, fairly low inclination, orbital period, and things like that. So this thing comes in, estimated originally at being 2 to 5 meters in size, predicted this is the trajectory, comes in here, and the various heights here. So it came in, landed in Sudan and blew up in the upper atmosphere. And people went out quickly to look for it, and this little black object here on this sort of hard desert pavement is one of the meteorites that came from it. And there's 600 fragments, and so it blew up, so there's about 10.5 kilos of it that have been recovered, and it now has the name of the Alma-Hattuseta meteorite. And it's a weird meteorite. It's like, if you wanted a nice C-type, well, it is sort of a C-type, but it's not one of the classic ones. It's an ungrouped one, which is basically, we have no idea what that is. And so it's a mixture of different carbonaceous chondrite type materials. In fact, every carbonaceous chondrite type that we know of exists in that meteorite. And so this is now thought of as being a regolith breccia. So it's something which accumulated on the surface of an asteroid out in the asteroid belt, which got pummeled, and everything out around it got pummeled and rained down different types of material and settled on this to become the surface of the asteroid, and then something came in and gave it an almighty great wallop and sends it off down into Earth-crossing orbit. So let's have a quick closer look at asteroids. So the reason, looking at them through a telescope is great, but they're fairly featureless. And so the big issue is when some of the missions started out was to get onto flybys. And you will note, if you look up Voyager in that font of all knowledge, Wikipedia, that Voyager was not interested in flying by asteroids. Gee, I wonder why. In fact, it was like, oh, we're entering the asteroid belt now, we're getting worried. And sort of they were worried they were actually going to encounter something. But lo and behold, it got to the other side and even got out of the solar system, both of them. So the flybys are very important. You get something for nothing. So if you've got a spacecraft out there and you go flying by this, then you can take images. Also allows you to test out your cameras and so forth. So Galileo on its way to Jupiter, 1989, went into orbit 1995. On the way, went past Gaspra and Ida, 1993. And here's Ida's little moonlit dactyl, which orbits it. So these look like solid rocky bodies. They look like monolithic structures. They don't look, they look like they're one piece of rock, which is interesting in itself, because we think of these things when we look at meteorites as being sediments in some way. So how do you get these big chunks of real estate which are solid bodies? Interesting point, not to be covered here. And then we have the 21 Lutetia flyby. This is on the Rosetta mission, so this is the one that went to P67. I'm not going to do the other two names. It's an M-type asteroid, so it's a metal asteroid. It's 100 kilometers, and so this is this is one of these asteroids that say, well, if we brought that back to Earth, how much money is that going to be worth? Because this has got all the platinum elements in it, which have all gone to Earth's core. It's full of this stuff. It's worth trillions and trillions of dollars until you start thinking, how much of this stuff do we actually need? Once everybody's got their own palladium for their catalytic converter in their car, it's worthless. And so the monetary value will quickly, if they ever decide to go and mine these things and bring them, or worse still, bring it back into Earth orbit, what can possibly go wrong? But interesting objects. The specific mission that went out to the asteroid belt to see something interesting was the Dawn mission. So it went to a trip out to Vesta and Ceres in the main asteroid belt, Launched in 2007, arrived in 2011, and then went on that it's arriving at Vesta. Departed Vesta, took off for Ceres in 2015, and then the primary mission ended there. And it's got to be a mission objective, and so if you're looking Ceres and Vesta, you've got one big muddy carbonaceous chondrite type parent body, and it turns out Vesta is a sort of a basaltic thing, which was igneous, and so it's dry. And so NASA's mantra is, or for the recent 20 years for exploration of the solar system, is follow the water, because that gives you the signs of life. And so you'll see that they're off to Europa, the Europa Clipper. Ooh, has that been funded or not? Maybe it hasn't. Might have been. So there's various missions going out to Jupiter moons and things like that proposed. And so the question is, how did Ceres stay wet and Vesta become dry? Which is just an excuse to go out there because it's a really neat thing to do. So Vesta is a weird object. It's actually the one asteroid which is just visible to the naked eye, 5.5. Not to my eyes, it ain't. I can tell you that much right now. Your eyes, maybe. And so it's a big asteroid. It's 525 kilometers across. It's got high density, about 3.5 grams per cubic centimeter. And it's the source of a family of meteorites called HED, and they're the ones which have these really strong dips, and this is associated with pyroxene. And so there's Vesta on the left, and then one of these HED meteorites, the eucrites, on the right there. So very characteristic. There's just no disputing that. So these are igneous rocks. Vesta itself is fairly beat up, so this is the best image that we had of Vesta through the Hubble Space Telescope before we went there. And even that, it's easy to tell that there's a big crater down this bottom region down here, and there's sort of like a bit of a remnant splash cone or something like this. But something like half of the asteroid is no longer there. And so this got absolutely crunched. And so that South Pole, there's a big 460 kilometre crater. What's wrong with that number? The diameter is only 525 kilometres, so you've basically been able to maintain a crater which is basically the same radius as the asteroid. So this thing should have just been, if this happened to one of the asteroids or the carbonaceous asteroids, it would have been smashed to smithereens, which is why we get stuff raining down into our solar system. The fact that it actually could survive this is related to the fact that it's a big basalt and it's tough. So this is dawn at Vesta, so Hubble image, best we could do. This is what you get when you get there. And so this is the real reasons for some of these flyby missions, just to be able to get these images of how these things are actually constructed. So this is one beat up asteroid. There's lots of craters on it. You can see this is the remnant of the crater around the South Pole. But there's all sorts of other things going on. There's all these compression rings around the equator, and it's very tempting to believe that these compression rings are what happened when there's 100 kilometre, well, whatever the size was. You usually think of about a tenth the size to cause the disruption of a. So there's still got to be a 40 kilometre asteroid if it's going to be 400 kilometres across. So this thing came smashing in, and it's compressed the rock all around the equator into these ridges. And there's various other things going on. Let's not worry about them. But now before it was left, Vesta was fully mapped, and you can these are the ridges around the outside, these compression rings. This is the major impact down on this bottom side. So the detail you get through these visits is really tremendous. The reason it gets smashed is that Vesta is at 2.36 AU, and it's just inside that 2.5 AU 3-to-1 ejection. So Jupiter swept something up and hurled it at Vesta and connected. So then onward to Ceres, and we saw this image before, so nothing much there. And then as we came in, I think this is one of the early photographs. The big thing about Ceres was that Dawn picked up these two headlights. And so, just imagine if Elon Musk had put his convertible up before this went, we found his convertible. So a couple of bright spots here, very cratered surface. It's really quite dark This does not come across because everybody wants to see what's going on. This is the close-up of these bright spots. It turns out that these are sort of like cryovolcanoes. They're liquid water coming up and depositing things like gypsum on the surface of the dwarf planet. And so there's potentially hydrothermal activity still going in series, who knows? But it'd be really good to find out if it was still going on. So the low albedo, this would be really quite dark, and that's what accentuates these bright spots. So Ceres is, if it's a carbonaceous chondrite, it's probably got a rocky core overlain by an icy mantle, 100 kilometres thick of water. And you can sort of pick this up by doing spacecraft orbits, because you can pick up the moment of inertia of the object you're actually going around. And so at 100 kilometres thick, that's 200 million cubic kilometres of water, and that's more than the freshwater supply on Earth. So you can imagine if one of these things got thrown down by Jupiter, smacked into the Earth after it formed and was hot and settling down a little bit, then you would end up with the oceans that we've got now. And we can do various tests and establish that the water we see in our oceans is very similar to the water that's actually on these bodies. It's not like comets. People think of icy comets as a good source of water. It's nothing like icy comets. It's going to be coming from these sort of asteroids. So as soon as a geologist sees that sort of thing, they want to say, well, we want a sample, please. We're going to go there and get some. And so there's various questions. What's happening on Ceres? Are C-types really carbonaceous chondrites? Why are carbonaceous chondrites rare when C-type asteroids are so common? And geochemists will always argue, well, go and get a sample and we'll give you the question. We'll give you the answer. Or if we give you the answer, then we'll give you a question to justify it. So if we want to go and get a sample, it's a long journey to the asteroid belt. So it took 4 years to get there for Dawn to get it around Vesta. A lot of these other flyby missions, what you're doing is you're accelerating. You've got to accelerate halfway, turn your spacecraft around, decelerate until you actually get into something which is roughly the same velocity at the position of the asteroid. So very complicated. It is rocket science. So Dawn took 4 years just to get to Vesta. You can imagine, well, it's going to turn around, it's going to come back. But if it was going to do that, it would have to carry more fuel. It would have taken longer than 4 years to get there in the first place. So it's a really non-trivial question, actually, getting out to the asteroid belt. They're talking about it now, but when they see the budget, we'll see. So the answer is to actually visit a near-Earth asteroid, get something which has already been thrown down close to us. So the near-Earth asteroids we visited around the early 2000s in the Near Shoemaker mission, and so that visited Mathilde, Gaspra, Ida, and finally, I'd say crashed, but it was about 1 metre per second low velocity impact onto the surface of Eros here. And the interesting about Eros was these sort of little mud pools that appear to be on the surface. So those are the target sort of asteroids we're looking at. There's about 35,000 near-Earth objects. It's quite a lot. But as soon as you start looking, well, we want to go there and we want to come back. So you're going to take all the high inclination orbits out. Things that have been chucked down from Jupiter quite often have high inclination sweeping around their orbits, so you can't get to them very easily. There's only about several tens, I think it was about 30 that people were describing 20 years ago when we were talking about actually doing these return missions. And the reason for doing that is if you can get it on Earth, very close to Earth's orbit, at least crossing Earth's orbit in the plane, these are the ones that might collide with us in the future and sort of do become interesting in that respect. But it means you've got the minimum delta V, minimum velocity change. Minimum velocity change means minimum force, which means minimum fuel. And so that means you can just sort of go out there, drive around, get onto it, and then just use the orbit to come back and deliver your sample back to Earth. So the first one done in this respect was the Japanese Aerospace Exploration Agency, JAXA mission, the Hayabusa mission, to get a sample from 25143 Itakawa. And so this was an asteroid which was only discovered in 1998. It's a small nearby thing. You can see the orbit up the top here. The blue's Earth, red's Mars, and Itokawa just comes down and crosses the Earth every once in a while. And so the hope is that you can wind up going around Earth orbit and then use Earth to go out a little bit, then slingshot yourself out into the Itokawa orbit, join up. And so the original mission was 5-6 years, something like that. So you've got to do a few orbits of the solar system before you can catch up with it. But this poor mission had a few issues along the way. So 2 of the 3 gyroscopes actually failed. So gyroscopes are used for controlling the attitude of the spacecraft, so just spinning wheels. The Japanese will say these are the only instruments that they did not get from Japan. They bought them from America. And 2 or 3 of them failed. If the 3rd one had failed, they wouldn't have been able to keep going with the mission. There was also a loss of control after the 2nd touchdown. There's uncontrolled firing thrusters, and so they couldn't communicate it with it for 6 months, and so the whole mission was delayed for 3 years. So the landing originally in 2007 was delayed in 2010. So this is the asteroid itself. So this is quite different from the monolithic asteroids. It's a rubble pile asteroid, 2 grams per cubic centimetre. It's got lots of porosity in it, so it's just an aggregation of a landslide in space. So this is like a 3-dimensional landslide. We went to Japan and we were invited to choose the landing site. And being a geologist, take the bright area and yeah, we'll take point A, that looks all right. And the engineers say, you can have point A. We're not going anywhere near this, it's too rough and rubbly. And yes, it is. There's like 10-metre boulders all over this area, so nobody's going to put a spacecraft down there. So they eventually targeted this point A for sampling and touched down twice potentially. The cameras on it were lousy. They didn't have GoPros then, so it's like the documentation was pretty ordinary. Anyway, despite issues, it came back to Earth in 2010, and the sample itself consisted of about 1,500 dust grains. So lo and behold, there was meant to be a gun which fires, stirs up the stuff and collects it. Didn't go off. And so there was accidental entrainment, which the sampler horn hit the surface, stuff went up, and thankfully was collected. These are all classic ordinary chondrite minerals: olivine, pyroxene, plagioclase, and this thing called trowelite, which is an iron sulfide. And the chemistry is a little bit different from iron sulfide, like pyrite you get on Earth, FeS2. This is close to pyrrhotite, which is the FeS type thing, but it's a little bit different. And the olivine and pyroxene compositions are quite distinct from Earth. They're actually up in so this diagram, this is really just the percentage of iron in the pyroxenes versus percentage of iron in the olivines. And the take-home message is that if we look at anything from Earth, it's down here. These guys are up here, which is in the field of the LL chondrites, which we're really grateful for because it was one of the H chondrites. It's like it's getting too close to Earth, and somebody said, well, it's not really asteroid, it's just something that got swept up off the lab floor. Anyway, it's an LL chondrite. Indisputably, it's actually quite a young body, so this thing is only 8 million years old, so that maybe when it aggregated only 8 million years ago. So these minerals that you can see over on this side are all 4.5 billion years old. But this aggregation and activity on these rubble piles means that it's grinding off surfaces or whatever, but it's a very young object. So with the success of Hayabusa 2 came to be. And so that was to go to a C-type asteroid. So we've been to the S-class, let's go to the C-types. And lift off in December 2014 at the asteroid, 2018, 19, and return in 2020. And then the Americans thought this is a really good idea, we're going to get in on this. And so they had the OSIRIS-REx mission to a B-type, which is really one of these sub-classifier categories of C-type, but let's not get into that. Asteroid Bennu in 2016 just got back last year, 2023. So these are different types of asteroids again. So Itokawa was only 500 meters long. These guys are about 1 kilometer across, but they're diamond shaped. If you look down on top of this, it's dead round. And so these are like spinning top asteroids. They've been re-aggregated and all this material has moved And down on the surface, it's rubbly and horrible, and so there's a lot of discussion about where we could potentially set down on the surface of the asteroid. And so there's so much consternation about it that there was a close pass-by, so down to 10 metres elevation, and then take off again. And let's think about this for a minute. But eventually, in early 2019, cameras have improved immeasurably. You will see a shadow come down here. So this is the wing, these are the solar panels. This is the sampler horn. So that touches down. As soon as that touches, bullet goes off, stuff comes up, and you can see it's sort of still raining around the spacecraft. So all of that, some of that material shoots up the sample horn into a container, and that's put into the sample return capsule. So what we got back was about 5 grams of black rocks, really black. Fragments and grains and dust, and it turns out, is a nice word, friable. This does not mean you stick it in your fry pan and cook it. What does friable mean?
Friable means that you don't stick it in your pan and cook it.
Kids been listening. So the answer is you don't stick it in the pan and cook it. So friable means that if you try to pick it up, it just falls apart in your hands. So if you try and pick it up with tweezers, anything, it was just, and of course we like making thin sections of things, and it's just really tricky on these sort of objects. So these are chemically related to carbonaceous chondrites. These are carbonaceous chondrites, but they have a specific association, which is one type of carbonaceous chondrites called the Ci chondrites, and the C means carbonaceous and the I means avuna, which is the type meteorite. And these are really important to geochemists because the abundances of the refractory elements, all the metals, all the non-metals and everything else, everything except hydrogen, carbon, nitrogen, oxygen, fluorine, and the noble gases is in an abundance which is very similar to what's in the sun. So this is potentially the primordial material that formed our solar system. There's only 10 of these things known as meteorites, and several of them are less than thumbnail size. And so there's a big issue about what these things actually represent and where they were. Are the Ci chondrite parent bodies really rare and things like that? They've all been altered both on their parent body, but they've also been altered by the terrestrial atmosphere, because these things were, even the falls, a couple of them were falls, they were stuck in museum drawers, and as soon as you stick them in a museum drawer, it's absorbing water from the atmosphere. But the Ryugu samples are absolutely pristine, and so we can start looking at things like organics, we can look at water, where the water lies, what this thing can actually tell us about potentially what was going into the sun. Now, the awful thing about these whole types of meteorites is they've been hydrated on the parent body, similar to what we see on Ceres, Eros, and things like that. There was water there. So what is Ryugu? If you look at it in detail, the dark stuff is serpentine, a hydrated magnesium silicate. That green stuff, you also see it as asbestos. If you go out to various serpentine mines, you see the nice chrysotile asbestos, which is a type of serpentine. And the lighter colours are dolomite, which is a carbonate, pyrrhotite, iron sulfide, and there's a few remnant olivine crystals, which are really quite interesting because every other chondrite has lots and lots of olivine, so why do these fine-grained things, the CIs, not have a lot? And so these were extensively hydrothermally altered in the early solar system at around about 45, 62 million years ago. So we can see that the solar system is roughly 45, 67 million years ago when things started collapsing, the first rocks were forming. So these are very early on. OSIRIS-REx at Bennu used a slightly different collection system. It just used an arm which goes down. It's like a vacuum cleaner, only vacuum cleaners don't work in space. And so they actually took the gas along with them and blew the gas in, so it got sucked up that way. And so with that technique, we've been able to collect about 120 grams of material, and it's also related to Ci chondrites. And because it was 2023, we're still doing the analyses. So the weird thing is, when we look at these things, 2 out of 2 C-type asteroids are rare Ci carbonaceous chondrites. What are the odds of that? I'm sure somebody can give me betting odds on that. and they wouldn't be very good. We would not have predicted that. We did not predict that. There are various other carbonaceous chondrites like Murchison. 120 kilograms fell in eastern Victoria in 1969, and in the same year, the Allende meteorite came down. There was 2 tons of stuff came down. So these things survived. What is going on? Why are the asteroids giving us CI chondrites and we're getting carbonaceous chondrites like this? So there's still some issues there. But it really is the fact that the CI that stuff from Rugu and Bennu are totally friable. So they just came in. So this is the advent of parents going to football games in the US, and this came in during a football game. So you can see this whatever the parent body was hitting the upper atmosphere is just absolutely being destroyed by that up there. So there's a shock wave which destroys it, then the friction and everything else. And so the chances are you might get just little grains of stuff coming down, but you may not. And so if all of these asteroids have CI, or a lot of them have CI-like material, it's just not going to survive that atmospheric re-entry. So out of the sample returns, we've been to an S-type asteroid. We know that it's a sample for ordinary chondrites, specifically the LL chondrites, but they're not the most common type. The most common ones are the H's and the L's. We still don't know quite what's going on with those parent bodies. The C-type asteroids are indeed parent bodies for carbonaceous chondrites, and all the implications therein for having organic molecules available, water available on Earth. Potential new missions, there's one flying pretty soon, must be taking off the next year or so, to Phobos, which is actually a captured asteroid. It's a moon of Mars, and potentially sampling the asteroid, maybe some of Mars got splashed up there as well. So the Japanese are sort of, well, maybe we can preempt the Mars sample return if that actually goes ahead. There's a comet sample return proposed. Last I saw it would launch in the 2030s. It's going to be expensive. You've got to speed up a lot. Comets are moving much faster than asteroids, so it's more expensive. People are talking about Vesta return, Ceres return, and if you're going to talk about that, you may as well talk about Jupiter moon return, and that will be really expensive. And remember I said somewhere along the line that space missions take a long time. It's like I've been associated with Hayabusa for 20 years on those 2 missions, and so these things, you're looking at the newest PhD students coming out to get involved with these things because they're going to spend their whole career doing this before they get back. And so you're doing this mission, you're not doing anything else, you're going to get poof, up in flames at the end if you're lucky. And of course we could just go back to the near-Earth asteroids and get stuff. So that's basically what I wanted to talk about tonight. I hope I haven't gone too far over. Yeah, a little bit, sorry. So let's just leave it up there and you can ask questions around that. You can read that as well as I can. I'll come back to it. Nothing like a launch.
All systems are ready. Main engine ignition. SRB ignition and liftoff.
So this spacecraft's about 50 meters long. It's not small.
We had a liftoff of the H2A launch vehicle number 26 with the Hayabusa 2 and 3 secondary payloads on board from the Tanegashima Space Center at 1:22:04 p.m.
こちらは固体ロケットブースター分離の模様です。
So it's going to let
サイ
go
ドについている SRBA が
the booster
今
rockets
落ちてい
detach.
きましたね。きれいに分離されているのが確認できます。
So this is one of the experiments they did on Hayabusa 2. This thing is an explosive head. And so shoots off and shoots a bullet into the surface. And I think the media at the time reported we were blowing up an asteroid. It's like, well, not quite. I just wanted to reveal the inner workings of the asteroid away from the top. So, and even then, the engineers wouldn't allow that. They would only allow it to be out over on the side here. And so that was the sampling of that thing. So let's put the conclusions back up again, and I'll take questions.
Amazing, Trevor. If you've got questions, we've already had a whole bunch come through. There is your QR code. Feel free to scan that and add your questions now. We have time for a few questions. While you're doing that, next month we are, of course, back again. We're going to go from the very big to the very small and talk about laser tweezers. We have the incredible Helena Rubinstein Dunlop, who is one of the real pioneers in this space, speaking. So make sure you join us next month. And of course, you can watch this video and almost all previous BrisScience videos on YouTube, which will go up in the next few days. So make sure you sign up to our mailing list to get all those details. Okay, questions. You ready? We've got a question from Bruce and a couple of others around when you mentioned the 200 parent bodies. And so they're asking, were the 200 large objects broken up into fragments for some reason, or why those bodies?
Yes.
Okay, no.
So we can recognise the chemistry and say, okay, this one matches that, that matches that. And so it may be a single parent body that's out there which is raining stuff down. But of those 200 parent bodies, some of those could be composites as well. So actually telling them apart. So we're just going on associations through the meteorites and say, how many individual types of body do we need? And so it's not an exact science on that, but we think there's around 200 that have come in.
Great. All right, question of definitions. Robert and John ask, when does an asteroid become a meteor, and what's the difference between comets and asteroids?
So yes, you have an asteroid. If it comes into the Earth's surface and you see that streak coming in, or it doesn't have to be the whole asteroid, it could be just one of the rocks off one of those asteroids. The streak of light is the meteor. Somebody goes out and picks it up at the end, it's a meteorite. So it becomes a rock. Most of the meteorites are meteorongs, but we'll put up with that. The other one...
Comets, pardon me.
Comets. So, yeah, scientists love classifying things. So it's either lumping or it's splitting. So effectively there's a continuum probably between asteroids being rocky bodies and comets being icy bodies. So most of the comets are coming from the outer solar system, beyond Neptune and the Kuiper Belt. And so those come in very rarely, and so they're dominated by ice. Even Pluto's dominated by ice. But there is rocky material associated with that. So the Rosetta mission, when they landed on that, no, they didn't land. Well, they did. It broke. So when they went to land on it, it fell over on that cliff face, which is weird in itself. Didn't sit upright. And so that's just, it's because you're at fairly low temperatures most of the orbit, that's minus, let's say, 200 degrees Celsius ice. And so that's rock hard. It really is rock. So effectively, ice becomes rock. But as it comes in, it's going to blade out. And so the specific things about comets, as they come from the outer solar system, their ice, once they start coming closer to the sun, they eject material, they warm up, water boils off, they have those beautiful tails and things like that. So I suppose that's the answer. Asteroids don't have tails.
Good answer. Okay, got time for two more questions. Vanessa wants to talk a little bit more about how we can learn from asteroids and meteorites even, about the composition of the primordial solar nebula and what this tells us about exoplanets and other areas.
So these are this is the only solar system we have samples of. So, we look out and we use telescopes to pick up exoplanets, and we can see those around other stars, and occasionally, you'll see a report of an atmospheric absorption feature which is related to water or something, or they've picked up an Earth-like planet. But this is the only solar system we can study really close up. And so the other thing we can look at beyond exoplanets is star formation. So if you look at star formation regions, you've got a star, it's heating up its surrounds, but most of those are so far away we really can't get the resolution with the telescopes. So again, it's our solar system which is telling us what's going on in terms of thermal history, how hot things got, what elements are coming and going in various processes and so forth. But that said, we don't know where most of the meteorites come from. We really don't understand the distribution of those meteorites, where those asteroidal parent bodies are in the solar system specifically, until we go out there and grab a sample. And so, the near-Earth asteroids are great because they're close by. But effectively, we need to get into the context of the asteroid belt. And so there's various proposals to do asteroid hoppers and do maybe 5 asteroids in one return mission. So you're not putting all your eggs in one basket. Well, you could do 6 and then you'd have a half dozen shell. But
It's like the old milk run flights.
yeah, that's right. So, just keep these going off in the background and keep them going, and we'll just keep farming them in and figuring out what's going on.
Excellent. Well, and that leaves my very last question, which is from Crystal, who asks, how would I try and find a meteorite?
So, find a desert. That's always a good thing to do.
Check.
And actually, Australia's pretty good for deserts. And so there's something like 1 fist-sized meteorite per square kilometre. So you've only got to theoretically march out a square kilometre, and I can guarantee you'll get a fist-sized meteorite.
Well, there's a weekend project for everyone. Trevor is looking for PhD students. Please give him a huge round of applause. Professor Trevor Ireland.
Thank you very much.
Please join us for some food and drink, and we'll see you all next month. Have a good night.